All right, good morning, everybody. Glad to see you're here safe. Hopefully your classmates trickle in. Days like today are kind of fun because snow down here and snow in the mountains. I have a 16-year-old that loves snowboarding, and he just got his license yesterday, which is just a little bit scary. He's probably going to ask me if he can drive up to Sundance after school today. And I think I'm going to say, no, I don't know. We'll see. Trials of a parent. But his interest in snowboarding has taught me a lot of interesting terms. For example, I know when you walk up to somebody on the slopes who's on a snowboard, the proper greeting is a saw. I don't know exactly what it means, but that's appropriate. All right. We are going to spend most of our time today still in our MO theory chapter. We're a little bit behind, and we need to get to the therefore what. Why have you been spending all this time trying to identify homo and lumo? I want to practice doing that before we get to the therefore what, and then we'll spend a bit of time on resonance, and then we need to move into acid-base chemistry. All of this is connected, even if you can't see it yet. Last time we looked at an alkene. We decided that the HOMO was the pi, carbon-carbon pi bond, and that the LUMO was the pi star. We made that decision based on the idea that carbon-carbon pi bonds are weaker than carbon-carbon sigma bonds because carbon-carbon pi bonds hold the electrons further away from the nucleus. Okay? In general, a weaker bond for us is going to mean that the bonding orbital is not as low in energy as stronger bonds are. Therefore, the pi orbital is a little bit higher in energy than the sigma bonding orbitals. A weaker bond will also mean that the corresponding anti-bonding orbital is lower in energy, which is why the carbon-carbon pi bond is the LUMO. It's a pretty good rule of thumb. It's not universal, but it's a pretty good rule of thumb that won't lead you astray that what's up here in the non-bonding orbitals is just a reflection of what's down here in the bonding orbitals. If the pi bonding orbital is highest in energy, you'd expect the pi star to be lower in energy. All right? So, HOMO versus LUMO. Now, why do we care about that? If a molecule is going to react as what we're going to call a nucleophile or a Lewis base, we're going to care about what the high energy electrons are. You learned in general chemistry that Lewis bases are electron donors. We don't mean that in the sense that you probably thought about it. We don't mean that an electron donor is going to toss away an electron and let it go. That's not really what we mean by electron donor. What we mean by electron donor is a molecule that has a high energy reactive pair of electrons. So, for a Lewis base, another word for a Lewis base is a nucleophile. I'll explain that term a little more in detail later. We care about what the high energy electrons are because those are going to be the ones that are involved in a reaction. So, we care about what the highest occupied molecular orbital is. For a Lewis acid is an electron acceptor. So it would make sense that Lewis acids, or in other words, another term we'll use for that is an electrophile, would have a low energy empty orbital that can accept a pair of electrons. So that's really why we care about HOMO versus LUMO, and I will show you how you can use that information to predict how molecules will react even in unfamiliar settings. Before we do that, I want to practice a little bit more on identifying HOMO versus LUMO. Some of these examples may be straight out of the MO theory study guide. Others may be a little bit more unfamiliar. So, no. Sure, let's draw large and terrible molecules. Okay, bromocyclohexane. Not shown are a bunch of CH bonds that you need to be aware of that are there. I guess now I will show them. That's terrible. Now, we can go through this the slow way, but I will eventually teach you the fast way to go through this. You can count, let's see, we've got, 11 carbon-hydrogen sigma bonds that we know are going to be filled with electrons. That tells us that there's also going to be 11 carbon-hydrogen sigma star antibonding orbitals that are going to be empty. I count 6 carbon-carbon sigma bonds that are filled. That means there's also going to be 6 carbon-carbon antibonding orbitals, sigma star orbitals that are empty. And then lastly, I've got this 1 carbon-bromine bond and a corresponding carbon-bromine sigma star. All right. So now if we wanted to, I've already told you that the bonding orbitals are filled and the antibonding orbitals are empty. You don't necessarily need to know that. If you want to, you can draw out a diagram where you have 11 lines down here for carbon-hydrogen sigma bonding orbitals and 11 lines up here. Okay, fine, we'll do that. Okay, so our dotted line here is going to represent the approximate and average energy of an atomic orbital that is not involved in a bond. AO is an abbreviation for an atomic orbital. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbon-hydrogen sigma bonding orbitals. Aha. All of you with pens and paper and or pencils can't copy and paste. So I'll pause to let you get caught up. No, I've got 6 carbon-carbon sigma bonding orbitals. A question that always comes up is, do I need to know whether or not the carbon-carbon sigma bonding orbitals are all the same energy, or if they are the same energy as the carbon-hydrogen sigma bonding orbitals? Not really, because they're actually not going to be either the HOMO or the LUMO in this case. So the actual ranking of the carbon-carbon and carbon-hydrogen bonding orbitals and antibonding orbitals isn't going to matter. So I'm going to draw just 6 lines down here. Now, if we actually did the calculation for this molecule, we would discover that all of those carbon-carbon bonds are not identical. They have different energies. All of the carbon-hydrogen bonds are not identical. They have different energies. But for our purposes, those differences in energy are going to be inconsequential. We're not really going to care. So it's fine just to say they're, on average, about the same energy. You can go look up in the back of the textbook in one of the appendices about bond energies, and you'll see that carbon-carbon and carbon-hydrogen bonds are generally shorter and a little bit more stable than carbon-carbon bonds. But what I'm telling you is, do not worry about the relative placement of carbon-hydrogen and carbon-carbon bonds. It's not going to matter. All right, we've accounted for everything other than the carbon-bromine bond. Now, without any experience, you're not necessarily going to know how a carbon-bromine bond ranks relative to a carbon-carbon bond. You can look it up in the appendix and you would see that the bond for a carbon-bromine sigma bond is less stable than a carbon-carbon bond. We will talk about why that is in chapter 2 and beyond. For right now, you can accept, perhaps on faith, or at least by looking something up in a table, that the carbon-bromine bond is weaker. It has to do with the large size of bromine, which means that the carbon-bromine bond is longer and weaker than a carbon-carbon bond. In any case, if I know that the carbon-bromine bond is weaker than a carbon-carbon or a carbon-hydrogen bond, what does that tell me about where the carbon-bromine bond should be? Should be a little bit higher in energy, right? Okay. And that tells me where should the antibonding orbital be. The bond's weaker, should be a little bit lower in energy. Now, what else am I forgetting? Lone pairs on bromine. Got to pay attention to those. Those are going to be important. Lone pairs are in non-bonding orbitals. They are in atomic orbitals that are not involved in a bond. So that means that I'm going to put them right there. These are the lone pairs, a cursive L to avoid confusion with the number 1, lone pairs on bromine. So now we can go ahead and fill the diagram with the available electrons. I've already sort of counted the electrons in my head. If you wanted to, you could do 2, 4, 6, 8, and so on to get the right total of electrons. But we would see if we did that all of the bonding orbitals are filled. Those CH bonds are filled, the CC bonds are filled, the CBr bond is filled, and then I have 3 lone pairs. All right? So then my decision as to what the HOMO and the LUMO are is trivial, right? The HOMO is the lone pairs, the LUMO is the carbon-bromine sigma star antibonding orbital. Okay? This is important because this tells you something about the reactivity of this molecule. We've learned now, if this molecule were going to be a Lewis base, the electrons that would react first would be the lone pairs on the bromine, always. Okay, the highest energy electrons there. If, on the other hand, this molecule were to be a Lewis acid, the lowest energy place for electrons to go is that sigma star. And tell me what happens when you fill a sigma star. You break corresponding sigma bonds. So already you're predicting some chemistry here, right? Chemistry in this, reactions in this class are going to involve forming and breaking bonds. If we were to have a nucleophile dump electrons into this orbital, we would break the carbon-bromine bond. And that is a reaction that we'll talk about in chapters 7 and 8. All right? One more quick example that we'll go through the slow way, and then I'll show you, as the study guide has pointed out, based on what we've learned, there's some shortcuts for identifying HOMO and LUMO where you can do it in 10 seconds or less instead of this business about drawing all the lines, okay? So let's just look at CH3 plus. I have 3 carbon hydrogen sigma bonding orbitals, which, based on the number of electrons I have, those should be filled. I have 3 carbon hydrogen antibonding orbitals, sigma antibonding orbitals that are empty. And then there's something else. To detect that, we need to remind ourselves that the geometry of this methyl cation is trigonal planar because it's surrounded by only 3 things, that it should therefore be sp2 hybridized, which means it comes with 3 sp2 orbitals and 1 p orbital. We've accounted for each of the sp2 orbitals in these carbon-hydrogen sigma bonds, right? We get each of those from overlap of an sp2 orbital on carbon with an s orbital on hydrogen to give you the new carbon-hydrogen sigma bond, right? So what's left over is a p orbital. And the p orbital is not involved in a bond, it's an atomic orbital. So if we show with energy how these orbitals rank, you've got the 3 carbon-hydrogen bonds here. About the energy of atomic orbitals, you have the p orbital, and then up here you have the 3 carbon-hydrogen sigma star antibonding orbitals. If I count electrons around this molecule, I have 2, 4, 6. That means these 3 are filled, but the p orbital, which is there, is empty. No electrons in it. It's still there. Remember, empty orbitals are still there. They're just the place where the next electrons would go if you had some. So now it becomes easy to say, okay, this p orbital is my LUMO. If I had to choose the highest occupied molecular orbital, it would be these carbon-hydrogen bonds. But I know that carbon-hydrogen bonds are pretty stable, so I'm probably not going to see this molecule react as a nucleophile, meaning, or a Lewis base. These electrons are low energy enough that they probably are not going to be involved in a reaction immediately. On the other hand, this empty p orbital is as low energy as any empty orbital we've seen so far. Yeah?
So in certain cases, you'll have like a low energy LUMO and a high energy HOMO. Could that be either Lewis acid or a Lewis base?
Right, in some molecules you'll have both a low energy LUMO and a high energy, highest occupied molecular orbital. And yes, some molecules can be both Lewis acids and Lewis bases. Yep, good. All right, yes?
So the only time that we're going to have unhybridized p orbitals is if carbon is bound to just three things or two things, so it's like linear to
So sure, one of the cases where you'll find an unhybridized empty p orbital is on a positively charged carbon. That's not the only time. Another one that's pretty common that you will see, we'll just change the element in the middle, but everything else sort of stays the same. Do you see how that would have an empty p orbital too? Yeah, in fact, the orbital picture for BH3 is exactly the same as for CH3. The only thing we've changed is we've taken one proton out of the nucleus. Yeah. So yeah, these are two cases where the LUMO is going to be this empty p orbital. And again, that's lower in energy than any of the antibonding orbitals are, because it's not involved in a bond. And so molecules that have empty p orbitals are generally very good Lewis acids. Another case that you'll see are aluminum-based compounds that are kind of like boron, but we won't worry about that because you won't see that really till 352. Okay, so we've been through this a couple of times. You've seen some different examples. The shortcut for highest occupied molecular orbitals is look for, first, lone pair electrons. If lone pair electrons are there, they're likely to be the highest occupied molecular orbital because they're not involved in bonds, and bonding stabilizes electrons. Second, look for pi bonds. If there's no lone pairs, look for pi bonds, because if there's no lone pairs, the next highest energy type of orbital is a pi orbital. What if there's no lone pairs or pi bonds? Well, we're going to see that molecules like that are generally not very good Lewis bases, so what the HOMO is probably doesn't matter. I realize that that is not comforting to you because you're envisioning a situation where I've told you it probably doesn't matter, and then I turn around on an exam and ask you a question where it does. So let me show you an example of why it doesn't matter. Let's look at this alkane. No lone pair electrons, no pi bonds, just carbon-hydrogen and carbon-carbon sigma bonds. So if we drew our energy diagram, you'd have a ton of lines down here and a ton of lines down here. It wouldn't make sense for me to ask you what the HOMO of the molecule is because I don't actually know. Is one of those carbon-hydrogen bonds or carbon-carbon bonds more reactive than the others? Probably. Do I care what it is? No. Why? Because that molecule, isobutane, is not really very reactive. You can use it as a solvent, and you can get it to do things, but not really as a Lewis acid or as a Lewis base. Okay? Yes?
Would there ever be a scenario where a CX element would be the HOMO, or is it always going to have electrons?
You're envisioning a CX bond being the HOMO. No, in general, those halides are going to have lone pairs. Yeah. Okay. The shortcut for the LUMO is first look for empty p orbital. That's not present that many times. You look for carbocations like this, positively charged on a trivalent carbon, or you look for boron or aluminum type compounds. Other than that, there's not that many cases where that will come up in this class. Second, you look for pi bonds. You think about pi stars. And if there's none of those, you think about carbon halide sigma stars. One question that comes up is, what if a molecule has both? A molecule that has both a pi star and a carbon halide sigma star might be reactive in more than one place. And I'm not going to ask you to decide. I know some of you are envisioning, I know you have nightmares about this kind of thing. A molecule like that. What's the HOMO? What's the LUMO? Well, you might be worried in terms of LUMO about the carbon-oxygen pi star, but you might also be worried about the carbon chloride sigma star. Guess what? You're right to be worried about both of them, and I'm not going to ask you to choose which one's going to be most reactive. In some ways, that will depend on what the other reactive partner is. Okay? So, I know that you may not want to trust me, but I'll sign here in blood to not, there's the dribbling blood, to don't worry about this. Worry about, now I realize now I have to define what not to worry about because about ranking a pi star versus a carbon halide sigma star, okay? If you don't see any of those, it, again, probably doesn't matter. That's your shortcut. Okay, so with that in mind, let's start to get to the therefore what, and look at some molecules, quickly deciding sort of HOMO versus LUMO. Okay, so here is molecule 1, and here is molecule 2. Dun, dun, dun. This is called, you don't care, but this is called hydroxide. Probably should learn that one at least so you know what we're talking about. This molecule happens to be called acetaldehyde. We'll learn about names of molecules later, but just so we know what to call them. For hydroxide, what would you say the HOMO was? Right, lone pair electrons on oxygen. The LUMO, you really only have one option, right? LUMO is just the oxygen-hydrogen antibonding orbital, but who cares? Because hydroxide's negatively charged. Probably if you had to pick between the two of these in this situation, who was going to be the Lewis acid and who was going to be the Lewis base, what would you choose for hydroxide? You'd probably choose to call this the Lewis base. How do you know that? You guessed because you've heard of hydroxide as a Bronsted base, and so you figured base here, base there, maybe that's good enough, right? Okay, that's decent intuition. A Lewis base is an electron donor, has a high energy pair of electrons. Lone pair is sort of as high energy as electrons can be. Plus, it's got a negative charge, so that's why that's a good guess. Another term for a Lewis base is a nucleophile. At this stage, I will tell you what the nucleophile is and what the electrophile is. In chapter 2 and beyond, we will develop some better intuition for making that decision. Okay, so now let's look at acetaldehyde. I will tell you that this is going to be the Lewis acid, or in other words, the electrophile, an electron acceptor. Lewis bases are what we're going to call electron rich. Lewis acids are what we're going to call electron poor. If you had to pick what the HOMO of acetaldehyde is, what would you say? Again, lone pairs on oxygen. I don't even have to worry about the carbon-oxygen pi bond because that's a bonding orbital. The oxygen lone pairs are going to be higher in energy than that. If I had to pick the LUMO, what would that look like? A carbon-oxygen pi star. Right, that's going to be lower in energy than the other antibonding orbitals because the carbon-oxygen pi bond is going to be weaker than any of the sigma bonds. All right, having decided that, at this stage it can be helpful to draw. I don't bother drawing what the orbital looks like for a lone pair because you just draw the two dots and then it's pretty obvious where the lone pair is. I do like to draw what the orbital looks like for the antibonding orbitals. So looking at this acetaldehyde from this perspective, we're sort of looking straight, straight down on the molecule's flat, the oxygen, carbon, and hydrogen, and this central carbon are all in the same plane, which means that the node for the pi star would be right here. We'd see a large lobe here and another lobe there. Then there'd be another node in the plane of the page with corresponding oppositely signed lobes below the plane of the page. And we can use shading to sort of communicate that. All right. So that's what the LUMO looks like for acetaldehyde. And then for the HOMO on hydroxide, it's just one of the non-bonding orbitals on oxygen. If you want to envision it as an sp3 hybridized orbital, that's fine. I'm not even going to draw it. Now, at this stage, we've identified Lewis base and a Lewis acid. We've identified HOMO and LUMO. We can now predict reactivity using the first and great commandment of, gray is not bold enough for writing out commandments. And it's still gray. Why is it still gray? All right. There we go. The first and great commandment of organic chemistry this didn't quite make it into the scriptures, is nucleophile attacks electrophile. Almost every reaction we deal with in OChem is going to be that way. The second commandment is like unto it. The HOMO of the nucleophile attacks the LUMO of the electrophile. In other words, we can form a new bond when we take the high energy electrons from the Lewis base or nucleophile and we dump them into the low energy empty orbital in the electrophile. Now for this pi star, I could actually have the oxygen attack the pi star in two different places, right? I could attack on the oxygen or I could attack on the carbon. May not be immediately clear which I should do, but you can use some chemical intuition to figure it out, things you already know. Tell me how carbon and oxygen differ, among many things. I'm hearing a word, electronegativity. Okay, that is a good word. What does that mean? Electronegativity. I'm hearing a couple of things out there, which is good. One of the things you learn is that electronegativity means how much an element pulls on electrons, which is okay. Elements don't know anything, so they don't know that they need to pull versus not. It actually has to do, I heard somebody say Z effective, has to do with how much charge there is in the nucleus. And as you go across a row of the periodic table from boron to carbon to oxygen to fluorine, the nucleus gets more charged, and therefore it pulls on each individual electron more tightly. Electronegativity literally just means how low in energy an electron is on that atom. Electrons on fluorine are lower in energy than electrons on oxygen, which are lower in energy than electrons on nitrogen, and so on. So that should tell you that oxygen, being more electronegative than carbon, should tell you what about this aldehyde? Let me just draw the structure again. If electrons are lower in energy on oxygen than they are on carbon, what does that tell me about the nature of this carbon-oxygen bond? There's a word, starts with P and ends in olarized. Wait a minute. It's polarized. That means that there should be extra electron density on oxygen, less electron density on carbon. Does that sound familiar? Did you learn that in Gen Chem? Maybe that's a 105 concept. Okay? Okay, so then put that together with what I just told you. Where should the nucleophile attack then, carbon or oxygen? The oxygen's electron rich. So, and the nucleophile has high energy electrons. So do you see how it would actually be repulsive for the oxygen to come here? For the nucleophile rather? Do you see how it would be repulsive for the nucleophile to attack at oxygen? Okay. In fact, it should be much more attractive for the nucleophile to attack the pi star at carbon. Now, that's one way of looking at it. Another way of looking at it that you aren't going to get from this class, if you want to know more, come take 552 in fall of 2024. How many of you are going to know? Nobody's going to do that. That's a grad level organic chemistry class. And in that class, I show you how actually, if you calculate how much LUMO is on oxygen versus carbon, more of it's on the carbon. So the nucleophile attacks the LUMO where most of it is, and most of it's on the carbon. You don't believe me, so now I'm going to show you. You did believe me, but I'm wasting time. Here's an aldehyde, a simpler aldehyde. I'm going to show you what the LUMO is. And you can see it's the pi star. And lo and behold, the pi star, more of it, it's bigger on the carbon than it is on the oxygen. So a nucleophile should be more attracted to the largest place where the LUMO is. Anyway, interesting aside. You don't need to know that, but there we go. Okay, so are we okay with the nucleophile attacking the aldehyde at the carbon? Makes sense? Now, the arrow indicates that the lone pair electrons on the nucleophile have made a new bond with the carbon. Anytime I overlap a filled orbital with an empty orbital, I make a new bond. But because the empty orbital that I made the new bond with is an antibonding orbital, I have to break the pi bond. And electrons from that pi bond move out onto that oxygen. So I can predict what the product of this reaction is. The sigma bonds are all in place. The pi bond broke and electrons from the pi bond moved out onto the oxygen. And then here is the new bond that I just barely made with what was my nucleophile. Okay? By the way, that is a 352 reaction. You're not going to get to that till 352, but this is a reaction that is called an addition reaction because I added the nucleophile to the electrophile and I made a new bond. Okay, yes?
Does it matter that you drew the hydroxide coming in on the side directly away from the oxygen?
Does it matter that the hydroxide is coming in on the side away from the oxygen? As opposed to where?
As opposed to say like between the oxygen and the C.
Okay, as opposed to here? For your purpose, for our purposes of this class, no. Though if you do the MO theory calculations, you see that that LUMO is angled back away in the place where I drew it. Yeah. Okay. Other questions? Yeah?
Just out of curiosity, when do you actually start calculating the math for fonts?
When do you start calculating what?
When do you start calculating the wave functions?
When do you start calculating the wave functions? Anytime you want. No, you can actually do this through programs that are available in the department. There's one called Gaussian that I'm clicking on just to show you, and you draw molecules and then you submit calculations. So if you wanted to learn how to do that, let's see, what classes would you take? I don't know. Come talk to me if you're interested in that, and I can make some recommendations. The best thing you could probably do is just get involved in somebody's research. Okay, want to do a few more examples of HOMO versus LUMO predicting reactions. The one we've done is actually pretty complicated. Let me show you a simpler one. Oh, that's terrible. BH3 and H2O. I'm going to go ahead and tell you that BH3 is your electrophile or Lewis acid. I'm going to go ahead and tell you that H2O is your nucleophile or Lewis base. Because for the Lewis base we care about the HOMO, I'm not going to ask you about the LUMO of water. Because for BH3, the electrophile, we care about what the LUMO is. I'm not going to ask you what the HOMO is. So you tell me, using your shortcuts in less than 10 seconds, what the HOMO and the LUMO are on BH3. Go ahead, and I'm going to time you. So go ahead and discuss it with your neighbors. You got, here's the stopwatch. Go, 10 seconds. Okay, fine. 5 more. 3, 2, 1, stop. Okay, what you got? What's the LUMO of BH3? Okay, I'm hearing p orbital. Does anybody have any other options? Why is it the p orbital? Because it is. Truth is independent and self-evident. It requires no explanation. Well, no. Because that's the lowest energy empty orbital that there is. The other empty orbitals are sigma star antibonding orbitals. The p orbital is not involved in a bond. It's therefore lower in energy than any of the antibonding orbitals. Okay, good. What do you got for water? Lone pair electrons on oxygen. Okay, from our perspective, BH3 is drawn flat. The empty p orbital would look something like this. There is a node in the plane of the page. We can show this with shading. Water can attack. HOMO attacks LUMO. Looks like us drawing an arrow from the electrons on water to boron, to the empty p orbital on boron. By the way, should it matter at all whether the water attacks from above or below? It actually can't matter. The above and below sides are identical. They've got opposite wave function signs, that's true. But remember, anytime we make a new bond, we're adding a filled orbital on water with an empty orbital on boron. The plus combination is going to give us the new bonding orbital, and the minus combination is going to get us the new anti-bonding orbital. The new molecule I make is going to look like this. I would need a positive formal charge on oxygen and a positive formal charge, and a negative formal charge on boron. But yeah, it can't matter which side I add to. Okay, and we'll see this. This will have consequences later on when we talk about, when we get to chapter 6 and 7. Yes?
What happens to the extra lone pair on oxygen?
Still there.
It's just hanging out.
Yeah. Still there, still not involved. Yep. All right, this is another example of an addition reaction. We add water to BH3. Let's do a substitution reaction. So methyl sulfide anion. This is an example of a nucleophile. It's negatively charged. And then let's use CH3I as our electrophile or Lewis acid. CH3S minus will be our nucleophile or Lewis base. For our nucleophile or Lewis base, we care about the HOMO. For our electrophile Lewis acid, we care about the LUMO. So, what do you got on the nucleophile? It's easy, right? Lone pairs on the heteroatom. By the way, organic chemists will refer to anything that's not carbon or hydrogen as a heteroatom. It's very carbon-hydrogen centric. We're very sorry about that, but it's sort of stuck. So if you hear me say heteroatom, that just means an atom other than carbon or hydrogen. All right, lone pairs on the sulfur. How about methyl iodide or CH3I? What should the LUMO be? Carbon iodide sigma star. Now you know that because I've told you that carbon iodide, carbon CX bonds other than fluorine, carbon chloride, carbon bromide, carbon iodide bonds are weak and long, and therefore their sigma star orbitals are lower in energy. Okay, let's actually draw that LUMO. A sigma star antibonding orbital, as we've said, looks like a dotted line here. You have smaller lobes pointing in between the two nuclei with opposite wave function sign. And then you have larger lobes pointing outward away from the space between the two nuclei. Right. Now, HOMO attacks LUMO. I've got actually two different places. We're going to have a similar situation as we had up here with our acid-aldehyde pi star. The LUMO is actually on two different atoms, okay? So let's talk about the two different options. Suppose I attack the LUMO at the carbon. What should happen to the carbon iodide bond? Should break, and the electrons only have one place to go, and that's on the iodide. So if I attack on carbon, I make a new carbon sulfur bond, which I'm going to highlight in red. And then the other thing I have is I minus, just on its own. Okay? If I did the other way, if I attacked on iodide, what I would make, I'm not going to draw the arrows for that, but I would make a new sulfur bond, sulfur iodide bond, and then I would get CH3 minus on its own. That would simply be the other option if S attacks I. At this stage, one of these may look better than the other to you, but at this stage, it may all look the same. In chapter 2, we're going to give you the tools to recognize that I minus is way more stable than CH3 minus. The way you do this actually as a preview is you draw the conjugate acid of your negatively charged group, which would be HI, or in the case of CH3 minus, it would just be CH4, right? That's the conjugate acid. Then you look up the pKa, which tells you how acidic something is. For HI, the pKa is minus 11. For CH3, the conjugate acid of CH3 minus, the pKa is 50. pKa is logarithmic units. The lower the pKa, the stronger the acid. Is that sounding vaguely familiar? So HI is 10 to the 61 times more acidic than CH4. That tells you if HI is that much more acidic than CH4, that tells you the conjugate base of HI is actually way more stable than the conjugate base of CH3. Yeah?
Sorry, if you were to do the electron movement with the arrows, if it attacks the eye, what would that look like?
Sure. Let's see. And that's where I would get this new Si bond and CH3 minus. Okay. The reason I didn't draw that is because that's not actually what happens. Based on what I've told you about the relative stability of I minus, that's a B there, way less stable, versus CH3 minus, it's actually way more favorable to do attack on carbon to get the product shown. All right, so this doesn't happen. Yes?
So for the, I saw like the reactants, there's the wedging dash formation.
Yeah.
Is there a way to tell what the products would be with wedging dash? Do we just
Oh, sure. I mean, right, I could draw, this is the new bond that I made. Yeah, it would look just like that.
basically the same?
Yep. We'll have more to say about this kind of reaction. This reaction is a substitution reaction. But, and so, but the basic idea of HOMO attacks LUMO, break a bond, is something that you now have the tools to predict. Yeah?
So wouldn't that just be the same idea as what you're talking about for
Exactly. It's the exact same concept as we talked about earlier with why, with our acetaldehyde electrophile, why the nucleophile attack carbon versus oxygen. There we used electronegativity. I didn't use electronegativity as a concept here because actually iodide isn't any more electronegative than carbon. They're actually pretty matched. So in order to figure that out, you sort of have to look at what the products would be and see that these products here are better and more stable than the alternative products. Okay, so I want to spend just a couple of minutes talking to you about resonance, and then next time we'll dive into chapter 3. So in the MO theory study guide, there is an example of resonance called the allyl anion. And what I intended to show you there is how MO theory and resonance get you to exactly the same conclusions. So we won't be able to do this in any detail in class. If you follow it along in the study guide, that's good enough. And maybe I'll say a little bit more next time. But what does resonance tell you about this molecule? How about the pi bond? Where is the pi bond? Resonance does not mean that that pi bond is hopping back and forth. Now I'm here, now I'm over there. It actually tells you that there is a hybrid structure that is the reality, and each of those resonance structures is an incomplete description of the overall structure of the molecule. Hybrid structures are difficult to draw, and so I don't typically draw them. I just draw resonance structures. Here, the dotted line literally means that the pi bond, what I will call as pi bond character across carbon 1, carbon 2, and carbon 3. That is a single electron, a single pair of electrons, 2 electrons, involved in what looks like a pi bond, but instead of being just between 2 atoms, it's between 3. All right? That's an example of electron delocalization. What does resonance tell you about the lone pair? Is it on carbon 1? Is it on carbon 3? Yes, it's on both of them simultaneously. I'm going to use the small Greek letter delta to represent that lone pair being on either of those two carbons. That delta minus tells you that, yes, I have the lone pair on C1 and C2. Sorry, I need to erase that. C1 and C3, never on C2. The electrons are not hopping back and forth. They are delocalized on both places. Now, I'll just mention at the beginning of class next time, I want you to look at the MO theory study guide one more time, but I want you to see how the MO theory picture exactly mirrors what these two conclusions are. And then we'll get into chapter 2. All right, thanks guys. See you next time.